Welcome everyone. We have already seen that neurons are responsible for transmitting electrical impulses. And we want to see how these electrical signals are actually generated and what is their nature. Okay, that is, what are the properties or characteristics of these electrical signals. And like I said in the previous presentation, electrical signals can be called electrochemical signals, can be called impulses, can be called nerve impulses, or can be called action potentials. So don't be confused if any of those terms are used. And for you to understand how action potentials are generated, you need to first know what happens if a neuron is not transmitting electrical impulses. The neuron is not transmitting impulses, it has what we call the resting membrane potential. So it is very important to understand the resting membrane potential because it is the changes that happen relating to the membrane potential that will result into an action potential. So when we talk about resting membrane potential, we're talking about the potential difference between the inside of the neuron and the outside of the neuron. Okay, so when we add the word resting membrane potential, then we are basically referring to the potential difference between the inside of the neuron and the outside of the neuron when there is no impulse that is being transmitted. And the resting membrane potential is between negative 60 millivolts to negative 70 millivolts. So the underlying point is that at resting membrane potential, the inside of the neuron is negative in relation to the outside, which is actually positive. And that is what we have here in the graph. That is the resting membrane potential. So what creates this resting membrane potential? The explanation lies with the ion channels that exist in the membrane of these neurons. So we have what we call ion channels that are called linkage channels. These ones are always open. That means that they allow ions to move freely. And then the gated channels are those that can only open when there is a stimuli. Okay, so when there is stimulation, then that is when they can open. So we call them gated channels. So one of the major contributor in terms of the resting membrane potential is the sodium potassium pump that exists in these membranes. There is an enzyme called sodium potassium ATPase that helps in pumping sodium ions out and then getting in potassium ions. And usually you have 3 potassium ions that enter, that are actually moved out, and then you have 2 potassium ions that actually move in. And this is a contributor to the chemical gradient that exists. So as a result of this sodium potassium pump, you'll have more sodium ions outside the neuron, and then you have more potassium ions inside the neuron. And that is why you'll have that negative charge inside and then positive charge outside. But the question that you should ask yourself is you have potassium and the sodium both being positively charged. So how come that we actually have a negative charge inside the neuron? The answer lies in the fact that the membrane of these neurons these membranes are actually more permeable to potassium. That means that more potassium goes out of the neuron. Okay, so it leaks more than the sodium ions that can enter. Okay, otherwise, if you have an equilibrium where the rate of entry of sodium ions is equal to the rate of exit of potassium ions, then you basically have a net charge of 0. But because the membrane is actually more permeable to potassium ions, you have more potassium ions leaving than the sodium ions that are actually entering. And eventually, you will have the inside being more negative compared to the outside. And that is basically what establishes the resting membrane potential. So in terms of the roles of ions, potassium appears to play an important role in establishing this resting membrane potential. But of course, potassium does not have what I can say a free gate where there is no impediment to its movement. You will have potassium also receiving some resistance in it trying to get out of the neuron. So that is because of one, you have a negative charge that is inside the neuron, and then you have this potassium getting out. And yet the potassium is actually positively charged, yet the inside is negatively charged. So you have that electrostatic attraction that tries to slow down the movement of potassium ions out. The other point is that the outside of the neuron is actually positive, and therefore, when potassium ions try to move outside, they will basically, these potassium ions will be repelled, and that also slows down the exit of potassium ions from the neurons. Okay, but overall, you'll have that net negative charge inside, and then the net positive charge outside the neuron. Okay, so for purposes of emphasis, you have the resting membrane potential being maintained by the sodium potassium pump, where we have three sodium ions that are pumped out for every 2 potassium ions that are pumped in. But remember that potassium ions face little resistance in terms of permeability. The membranes are more permeable to potassium. So more potassium ions move out, and that is what creates the negative charge. When also talking about the membrane potentials, we sometimes talk about the negative ions that are inside the neurons that also contribute to that the negative charge. So these are often proteins that are trapped inside. They also contribute to the internal negativity of the neuron.